How do we use L'Hopital's rule to evaluate limits? In this video, I will give you guys 14 examples, so check this out. For the first one, we have the limit as x approaching 0, x minus sin x over x minus tangent x. And we shall always plug in this number into all the x's first to see what happens. And when we do that, we get 0 minus sin 0, which is just 0, over 0 minus tangent 0, tangent 0 is 0. So in fact, we have 0 over 0. That's actually good news because we can just use L'Hopital's rule. And to do so, we'll just differentiate the top and then differentiate the bottom. Okay, so again, this is a 0 over 0 case. We can use L'Hopital's rule, and then we will get the limit as x approaching 0. Differentiate the top, we get 1 minus cosine x, and then differentiate the bottom, we get 1 minus secant square x. And notice this right here, it's not a quotient rule. It's really just you differentiate the top and you differentiate the bottom. Because the idea is that instead of comparing the original top and bottom, we are comparing the derivatives of the top and also the derivative of the bottom. Alright, so that's what you have. And here's a small trouble. If we put 0 into cosine, we get 1. 1 minus 1 is 0. If we put 0 into secant square, that's also 1. 1 minus 1 is 0. But you know what? We can do L'Hopital's rule. Or we can just do some cancellations. So it's kind of like up to you. Well, this right here is 1 over cosine square. So what we can do is, let's just multiply the top and bottom by cosine square x. We're just going to do some, cancellations. So when we do that, you see that this is just going to be the limit as x approaching 0. On the top, I'm not going to multiply out. I will show you why. This is still 1 minus cosine x and then times cosine square. But when we do that, this times this is cosine square x, and then this times that is just minus 1. Can we factor this? Yes. When we do that, we get cosine x minus 1 times cosine x plus 1. Well, this is cosine x minus 1. This is 1 minus cosine x. They are almost the same. What we can do is, well, just factor out a negative from here, so we can reverse the order of the subtraction, so we can put this as cosine x minus 1. What good does this do? Very good, right? Okay, let me just get my blue marker. Cancel, cancel, life is wonderful. And now we can see that on the top we just have the negative and then cosine square x over that. So we can just go ahead and plug in 0 into here. So we get negative and then cosine square, and the x is 0 over cosine x again is 0 and then plus 1. And then just compute it. Cosine 0 is 1, square that's still 1, but that's negative 1 on the top, and then over 1 plus 1, which is 2. And ladies and gentlemen, the answer is just negative 1/2. Okay, cool. Now for the second one. Plugging 0, yes, inverse tangent of 0 is 0, and then square that's still 0, and then over 0. So yes, 0 over 0. Okay, let's go ahead and differentiate the top and differentiate the bottom. But be careful, you should always check if you have 0 over 0 or not, right? So here, 0 over 0, we can use L'Hopital's. Okay, this is the limit as x approaching 0. The derivative of the top, well, we'll just bring the 2 to the front. I'll put this down in blue so that it stands out better. And then minus 1. So we get 2 times inverse tangent of x. But we will have to multiply by the derivative of this because of the chain rule. So multiply by 1 over 1 plus x squared. And you see that on the bottom, the derivative of x is just equal to 1. So that's very nice. And now we can just plug in 0 into this x and that x. And it doesn't give us any trouble. Life is just so wonderful. You see this is 2 inverse tangent of 0 over 1 plus 0 squared. On the top is 0, on the bottom is 1. 0 over 1, we can conclude that is 0, and then we are done. Now continue with number 3, we have the limit as x approaching 2 plus. And remember, this right here just means that we are approaching 2 from the right hand side. And you can think about x is like a number just a little bit bigger than 2, such as 2.0001. Okay, so as usual, we should put this number into all the x's. And when we do that, 2 to the third power is 8, and then minus 8 is 0. But this right here, just technically a little bit bigger than 8 because of the plus sign. So inside here, we actually get 0 plus because it's just a little bit bigger than 0. And then we have the ln. On the bottom, do the same thing. This is 4 minus 6 plus 2. We get 0, but because of this plus, it's actually a little bit bigger than 0. You can work that out on your own. And we get ln on the top here. This is approaching negative infinity. On the bottom, we also approach negative infinity. So this is indeterminate, but it's actually not so bad because at least we can use L'Hopital's rule right away. But you should always do the check, all right? And the negative doesn't really matter because we just care about the limit form. So right here, let's go ahead and just differentiate the top and then differentiate the bottom. And as a reminder, this is from the infinity over infinity form, and then let's write down. We are using L'Hopital's rule. And this is the limit as x approaching 2 plus. Okay, do the derivative. The derivative of this, ln of something, you just put it inside on the bottom. So here we get x to the third power minus 8. And then don't forget the chain rule. So multiply by the derivative of this, which is 3x squared. And then do the same thing on the bottom. The derivative of this, we put this on the bottom right here. So x squared minus 3x plus 2. And then do the chain rule. Yeah, and we get 2x minus 3. All right, so far so good. But the problem is, if we put 2 into all the x's, we are going to run into trouble again because you see we get a 0 on the bottom and then 0 on the bottom. So in fact, we have two choices. The first choice is that we can just clean the complex fraction and then use L'Hopital's rule again. Or notice that this right here is actually factorable. Likewise, this is also factorable. So you can also just kind of factor things out and cancel things out. And let's do that. I'm going to do both. How's that? I'm going to do both. So I'm going to factor it first for you guys. Okay, we have one fraction divided by the other, which is the same as multiplied by the reciprocal of the second. So let me write this down first. We have 3x squared. And then to factor x to the third power minus 2 to the third power, right, for the 8. This right here, by the difference of 2 cubes, we get x minus 2 times x squared plus 2x and then plus 4. And perhaps I will remind you guys the formula real quick. Again, the formula is when we have a to the third power minus b to the third power, this right here is a minus b times a squared plus, right, plus, I don't know why I look at my own work to write down the formula, I have no idea, but plus ab, and then lastly we add b squared. So you see, a was the x and then b is the 2, so that's why we have all that. Okay, so that's what we have, and now we are going to do the reciprocal. So I'm going to put this on the top, and when we factor this, we get just x minus 2 times x minus 1. So it's actually really nice. And on the bottom here, we have 2x minus 3. And now we see this and that cancel, which is pretty nice. And we can just now plug in the 2 into all the x's because there's no like 0 over 0 or infinity over infinity anymore because in fact we canceled that already. So that's the beauty. So let me just write that down for you guys. We have 3 times, just plugging a 2 is okay. So we have that and then times 2 minus 1 over, and then here we get 2 squared plus 2 times 2 plus 4. And then 2 times 2 and then minus 3. Oh my god, it's a big number. Okay, let's see. On the top, this is 4 times 3, which is 12, and that's 1, so we just have 12 over, luckily here, this is also 1, so this is 4 plus 4 plus 4. You're kidding me. 12 over 12, so this is equal to 1. Yeah. Wow. Infinity over infinity, that gives us 1. That's not always true. Not always true. Not always true. Because for this one, have a look. When x is approaching infinity, on the top we get infinity. On the bottom, ln infinity is infinity. Raised to a third power is still infinity. So this is also an infinity over infinity case. Well, we can do L'Hopital's rule, so I'll write it down right here. So again, infinity over infinity, using L'Hopital's rule, differentiate the top, and then differentiate the bottom. Okay, so this is the limit as x approaching infinity. Derivative of x, oh my god, that's just 1. And then differentiating this, well, use a blue marker. Put this in the front, minus 1, we get 3 times ln x to the second power. But don't forget, we will have to multiply by the derivative inside. So multiply by 1 over x. Oh my god, we will have to put this on the top, right? So in fact, this is kind of cool, kind of not. Okay, so when we do that, we are looking at the limit as x approaching infinity, and we have x on the top over 3 parentheses ln x squared. Same thing, when we put infinity here and here, we get infinity over infinity. So yes, L'Hopital's rule again. And let me just do it with red. So differentiate this, and we can use L'Hopital's rule as many times as we would like if we notice that we are making progress. We are making progress because you see that the powers is getting smaller and smaller. But anyway, L'Hopital's rule, and here we have the infinity over infinity situation, so perhaps I'll write that down just to make it clear. Alright, so we are getting limit as x approaching infinity again. Same thing, oh my god, this is 1. And this right here, blue marker again, put this to the front, minus 1, and we get 6 parentheses ln x to the first power times the derivative of this, which is 1 over x. Oh my god, yes, we put this on the top again, right? So this right here, we get the limit as x approaching infinity. We are looking at x over 6 ln x. And by now you can actually use what we call the list, but that's a secret weapon. I don't want to use that yet, because for this, I just want to practice L'Hopital's rule with you guys. Anyway, infinity over infinity, do the L'Hopital's rule one more time. Oh my god. Right here, what do we get? We get the limit as x approaching infinity, and then right here, we will just have 1 on the top. And by the way, just to show work, 1 on the top, and then the derivative of this is 6 over x. Alright, this right here we can just do the reciprocal. So in fact, this right here it's the same as the limit as x approaching infinity, x over 6. Finally, infinity on the top, over 6, which is just a finite number, we end up with infinity. Oh my god, you see, infinity over infinity, it gives us infinity. And earlier, yeah, it did give us 1. But infinity over infinity, we really don't know what happens unless we do more work, right? Number 5. Okay, the limit as x goes to infinity of all that. And let me just tell you, in this case, we will end up with infinity over infinity. I'm going to show you guys the L'Hopital's rule first. And we can also do this the pre-calculus way, alright? Okay, so because we have infinity over infinity, so let me just indicate that real quick right here. And then we are using L'Hopital's rule. So go ahead and just differentiate the top and then differentiate the bottom. Alright, this is the limit as x approaching infinity, and we get the derivative, which is 2x and then plus 4, done. On the bottom, we have 10x and then minus 1, done. And by the way though, do not factor anything. You could, but like, don't factor anything. Just differentiate, it's okay. And now this is what we have. And when we plug in infinity, we still get infinity over infinity, right? Well, let's go ahead and just do L'Hopital's rule one more time. So here, and also here, and we get, alright, again, let me just indicate that real quick. This is the limit as x approaching infinity, and we just get 2 on the top over 10 on the bottom. No more x, right? And you see 2 over 10, of course, is 1 over 5. So the answer is just equal to 1 over 5, and then we are done. But imagine if this was x to the 10th power and then 5x to the 10th power, do we really want to differentiate this like 10 times? I don't think I want to do that. So let's do the pre-calculus way. And if you guys, whenever we have a rational function like this, just go ahead and do this way. It's much better, right? So what's the pre-calculus way? Let's look at the limit as x approaching infinity. This only works when x is approaching infinity, and then right here we have a rational function. On the top is x to the second plus 4x and then plus 3 over 5x squared minus x minus 4. Pre-calculus way. Pick the biggest power of x on the top, which is this. Pick the biggest power x on the bottom, which is that. X squared, they are the same power, so they cancel, and we'll just get 1 over 5. Done. So, ladies and gentlemen, yeah, this is the pre-calculus way to do it. And in fact, the reason I picked the biggest power is because it's the dominating part. And in fact, this works because we have the L'Hopital's rule to back us up, right? So, the good old pre-calculus way. If you do this on my test, it's totally okay. Now, let's look at this. When we put infinity into here and here, e to the infinity is infinity, plus 1 is still infinity, ln infinity is infinity. On the bottom, we also get infinity. So, this is an infinity over infinity case. Alright, and then L'Hopital's rule in action. So, d dx, d dx. Okay, this is the limit as x approaching infinity. On the bottom, we have 4. On the top, when we differentiate this, put this on the bottom, which is e to the x plus 1. And don't forget the chain rule multiplied by the derivative inside, which is e to the x. That's pretty much it. Okay, so we have an over 4. So what we can do is, depends on how you like to simplify your complex fraction. You can multiply the top and bottom by this denominator, or you can just kind of drag this, put it here. That's all. So we are really just having the limit as x approaching infinity. This is the same as e to the x over 4 times that. And again, just real quick, the reason is just that we are multiplying the top and bottom by this denominator so that we can fix the lowest, we can fix the complex fraction situation. So that's exactly how we get that. And of course, you don't have to show the steps every single time. But you see, we have infinity here, infinity here, so it's infinity over infinity. So let's go ahead and do L'Hopital's rule. And by the way, we have to take the derivative right here, right? It might be a better idea for us to distribute the 4. So in fact, here, let's look at this as 4e to the x plus 4. And the truth is, you can actually tell the answer is 1 over 4 already. But let me just go through the L'Hopital's rule and I'll tell you guys how we can do that. So infinity over infinity, LH, differentiate the top, and then differentiate the bottom. Here we have the limit as x approaching infinity. E to the x never dies, still e to the x. On the bottom, this 4 goes away. Here we have 4e to the x. The truth is, you see how we have e to the x and also 4e to the x. The plus 4 doesn't matter. When you are doing limits, you can actually just ignore the constant terms. You just need to pick out the dominating parts. In the pre-calculus, we talk about the biggest power of x because that's a dominating part when we have a rational function. But the truth is right here, when we have the biggest power or the biggest function, just pick that, and then you can just compare them. That's all. So you see, right here, that's what we have, and then e to the x cancel, and we just have 1 over 4. Ladies and gentlemen, the answer is just nicely equal to 1 over 4. And then we're done. Okay, for number 7 and number 8, I will say that they are the exciting ones. Have a look. Here we have the limit as x approaching 1 plus. And remember, 1 plus means we are approaching 1 from the right hand side. You can think about x as 1.0001. Keep in mind, x is not exactly equal to 1. And here we have x raised to the power of 1 over x minus 1. Well, as usual, let's putting this into all the x's. But I'm going to really distinguish this. This right here will be written in red. So here we get 1, and this right here will be written in blue. And we have 1 over, this is 1, and then minus 1. Remember the red 1 right here is not exactly equal to 1. But this is the usual things that we do when we want to just plug in and see what happens. And now let's continue. 1 minus 1 is 0, so we know this right here, we have the 1, and then 1 over 0. and 1 over 0, because both of them are positive, we can say that that part goes to infinity. And you see, we end up with 1 to the infinity's power, and people usually say, isn't 1 to any power is just equal to 1? So shouldn't the answer just be equal to 1? No, that's not true. Because what we are really doing here is that this 1, it's not exactly equal to 1. This is just our bad habit. Technically, we should be putting down 1 plus along the way, but nobody really does that. So you really have to remember, 1 to the infinity's power is an indeterminate form. We cannot draw a conclusion right away. And if you really want, you can emphasize that this is 1 plus, 1 plus, and this is 1 plus. 1 plus minus 1 is 0 plus, and that's how we get the past infinity. And then right here, I will write it as 1 plus, and then raised to the infinity's power. So that's what is really happening. So just keep that in mind. But anyway, what exactly is the answer? That's the main question, right? And how exactly do we do it? 1 to the infinity's power is one of the little kids that we don't like for the indeterminate family. So let's make it happen to find the parents, either 0 over 0 or infinity over infinity. We really don't like to have x for the base. We like to have base e. So this is how we can do it. This is just the algebra for now. So the limit as x approaching 1 plus. Look at this x. We really want to have base e. But you see, e and what else will give us x? Namely its inverse. So we just have to compose it with ln and then put the x right here. This and that cancel will give us the x back. This is how we can really be using the base e. And we will take this raised to that power, which is 1 over x minus 1. Now we can just multiply these powers together, so we get the limit as x approaching 1 plus, and then this is just e raised to this over that power, so ln x over x minus 1 power. Well, when x is approaching 1 plus, this is the function part, right? Because now the base is just e. So look at this, put 1 in here, ln 1 is 0, and then 1 minus 1 is also 0. So we can use L'Hopital's rule right here. And the truth is, when we are taking limit of this, we can just focus on the limit of that, and then in the end, we do e to that power. That's the idea. So let me write this down for you guys. E is still right here, but we will be focusing on this limit here. So we take the limit as x approaching 1 plus, and then here we have ln x over x minus 1. Okay? For the blue part, we do L'Hopital's rule. So do this, do that, and you will see this right here. It's going to give us the limit as x approaching 1 plus, and we get 1 over x over 1, which is very nice. Alright, so let me just put on e right here. But you see, when x is approaching 1 plus, we put it here. This part is just going to be 1. So the blue part is 1, right? And altogether, we'll just have e to the first power. And that's of course just e. So ladies and gentlemen, the answer is e. Yeah. So in this case, you see, originally we had a 1 to the infinity's power indeterminate form. Okay? Originally we have the 1 to the infinity's power form, but in the end we end up with a number that's not e. Cool, huh? So be really careful. That's all I'm saying. Alright, for this, it has similar flavor, and I'm just going to go through this real quick because I went through that in details earlier already. Here, 0 plus. So remember, x is not exactly equal to 0. When we put 0 plus in here, we get 0, right? And then this is 1 over, this is 1 plus ln 0 plus. Okay, let me indicate that because ln for that. This right here, we can draw a conclusion. The base is still 0, 1 over, this is 1. ln 0 plus is negative infinity. And then you see that this right here, 1 minus infinity is still infinity. So we get 0, and then we get 1 over negative infinity. 1 over negative infinity is 0. So this right here gives us 0 to the 0th power. Yeah, another indeterminate form, all right? And again, this right here, we cannot draw conclusion because the base is not exactly equal to 0. So that's all I'm saying. So that's the detail. I still went through the detail, but anyway, this is the 0 over 0 indeterminate form. They have similar flavor. Let's go through the computation. X for the base. Okay, so again, this is the limit as x approaching 0 plus. Look at this as e to the ln x power and then raised to the 1 over 1 plus ln x power. Multiply the powers, we get the limit as x approaching 0 plus e for the base. This and that multiply, and we can just have ln x on the top over 1 plus ln x. Same thing as what we did over there. We can just take the limit right here. So we get e, and then let's focus on this limit as x approaching 0 plus, and then this is ln x over 1 plus ln x. So you can kind of do limits inside out, provided that if the function is continuous. That's what we have been doing. Yeah, just like that. Okay, so right here, again, do L'Hopital's rule, huh? So d dx can, this is going to give us, let me see, this is going to give us limit as x approaching 0 plus. This is 1 over x over 1 over x. Okay? But you see, 1 over x, you reduce this first. Right? You reduce this first. So, in fact, this right here is e to the power. But because you have to reduce this first, you actually just get 1. So this right here is once again e to the first power. And again, it gives you 1. I mean, it gives you e. Alright, so this right here took us some time. Yeah, crazy, huh? For number 9, we have the limit as x approaching 1 plus. So we know the deal. Go ahead and plug in 1 plus into all the x's. So let's see, we get 1 plus over 1 plus minus 1 and then minus 1 over ln of 1 plus. So this right here goes to 1 plus, and then on the bottom, 1 minus 1 is 0, but this is bigger, so it's technically a little bit bigger than 0. So put on 0 plus. And then this is minus 1 over ln 1 is 0, but if this is a little bit bigger than 1, then we end up with a little bit bigger than 0. And you see, both of these are positive, so we get infinity. And likewise, this right here, both of them are positive, so you get infinity. Whenever we have a non-zero number over like a 0, when you are doing limits, it's either positive infinity or negative infinity. You just have to work out the sign. But infinity minus infinity, unfortunately, we cannot draw any conclusion. This is again an indeterminate form. The conclusion that we can draw is we have to do more work. But do not put down do more work on the test. We really have to do the work to see the answer. Alright, so let me just indicate that infinity minus infinity. Do not say it's 0. We don't know. Let's see. We have this minus that. Why don't we combine the fractions? So let's multiply this by ln x, and then multiply this by x minus 1, x minus 1. So we get the limit as x approaching 1 plus. On the bottom, we just have x minus 1 times ln x. On the top, we have x ln x minus, and perhaps minus times this, right? So distribute that, minus x and then plus 1. Yeah. Now, when we put 1 plus into all the x's, we can check. On the bottom, we get 0. You can check. And then on the top, we get 0. Just go ahead and check. Good. This is 0 over 0. We can do L'Hopital's rule. So, this is what I mean that if indeterminate form, right? If you get one of those kids, if the kid is annoying you, you will just have to go find the parents. And this time we got 0 over 0, so we can use L'Hopital's rule. Okay, differentiate the top and also differentiate the bottom. Okay, this is the limit as x approaching 1 plus. Derivative, well, we need to use the product rule. first function times the derivative of the second plus the second function times the derivative of the first. And then the derivative of minus x is just minus 1. On the bottom, we also need to use the product rule. Keep the first function times the derivative of the second plus the second function times the derivative of the first, which is 1. If we put 1 into all the x, unfortunately, we get 0 on the top and 0 on the bottom. So we will have to go through this again. But we see that this is just 1. 1 minus 1, of course, they cancel out. And right here, perhaps we can distribute this before we take the derivative. So let's go ahead and write this down one more time. The limit as x approaching 1 plus. And maybe after this video, you guys can let me know if you guys like limits more or integrations more. But anyway, ln x, this times that is just 1, this times this. I'm going to write it as x to the negative 1 power because it's easier for us to do the derivative like this. And then we also have the ln x. Alright, we get 0 over 0, so L'Hopital's rule one more time. So put down ddx and another ddx. Okay, so let me write this down. 0 over 0, L'Hopital's rule, and then this is the limit as x approaching 1 plus. On the top, we get 1 over x. On the bottom, this is going to be 0. The derivative of this, we put the negative in the front, so it's positive. Minus 1 here, so it's x to the negative 2, which is 1 over x to the second. And then the derivative of that is just 1 over x. And right here it's good because we don't have to simplify anything because x is just going to be plugged in as 1. So after we do that, we get 1 on the top, and then 1 plus 1, which is 2 on the bottom. Wow! Infinity minus infinity in indeterminate form gives us 1/2. Quite unbelievable, huh? Now, let's look at number 10. It has similar flavor. If we put 0 plus, you can see this is going to be 1 over 0 plus as well. Likewise that, so it's infinity minus infinity. So again, this is also infinity minus infinity indeterminate form. So what do we do? Let's combine the fractions just like that and see what happens. So let's multiply this right here by x and then x right here. And let's multiply this by sin x and likewise here. So we get the limit as x approaching 0 plus. On the bottom, we just have x times sin x. On the top, we have x minus sin x. And now you see, when you put in 0 into all the x's, we get 0 over 0. So we can use L'Hopital's rule. So go ahead and put down ddx and then also ddx. Okay, this is 0 over 0 case, and then we're using L'Hopital's rule. And then we have the limit as x approaching 0 plus. On the bottom, let's do the product rule. So first we get x times the derivative of that, which is cosine x. And then we add the second function, which is sin x, times the derivative of the first, which is 1. On the top, we get 1 minus the derivative of that, which is just going to be cosine x. I will have to tell you guys, we have to use L'Hopital's rule again because it's again 0 over 0. But it's okay because we can just differentiate this real quick and likewise do the same down here. Okay, here we get again 0 over 0, L'Hopital's rule, the limit as x approaching 0 plus. Okay, so let's differentiate the top first. We get sin x. And on the bottom, right here, we have x times the derivative of the second, which is going to be negative sin x, plus the second function, which is cosine x times the derivative of the first. And then right here, we just add the derivative of that, which is cosine x. Can we plug in 0 now? Yes, because when we do that, on the top, we get 0 over this right here. When x is 0, you get 0. And then cosine x, when x is 0, is 1. So we just add 1, and then we add another cosine x, which is when x is 0, it's another 1. So ladies and gentlemen, altogether we get 0. And this is perhaps the one that you guys were waiting for, right? Infinity minus infinity, you get 0. But not all the time. Earlier it was 1/2. Okay, number 11, we have the limit as x approaching infinity of this minus that. Just real quick, when we plug in infinity into here and here, we will end up with infinity minus infinity. So another case, right? And let's see what this will give us. And let me just put that down right here real quick. Okay, how can we combine this now? There's no fraction. Well, this is a subtraction of two logarithms, so we can just combine the logarithms together. This right here will give us the limit as x approaching infinity. Just put down one natural log, and then we'll just have this. So x squared minus 1 over that. Yeah, very nice. And now check this out. We are taking limit, and we just have to focus on the inside first, right? So we can just put the ln on the outside, and that's exactly what we did earlier too. One of the questions, not like the earlier. So I'm going to put on ln, and then I will look at the limit as x approaching infinity, and then we have x squared minus 1 over x to the third power minus 1. So that's what we have. And the technical detail for this is that because natural log is a continuous function, that's why we can do this. And now this is just a rational function. You can do L'Hopital's rule because it's infinity over infinity. But we can also do the pre-calculus way. And that's just going to be, we look at the highest power of x right here, likewise here. Then that reduces to 1 over x. And when x goes to infinity, that is just equal to 0. So right here, we get ln of 0. But be really careful. Technically, this right here is approaching 0 and it's from the right hand side, meaning that this is a positive 0, like that. So ln 0 plus, we get negative infinity. Yep, that will be the answer for that. So infinity minus infinity, we get negative infinity. Cool, huh? And the truth is, this function is actually much bigger than that. That's why we end up with negative infinity. For this one though, how can we combine this? This is not natural log. But don't worry, we have a square root, right? Just like the good old Cal1 days, when we have square roots, let's multiply the top and bottom by its conjugate. That's why I didn't put on parentheses right here. Anyway, I'm going to multiply this right here by the conjugate, which is square root of x squared plus 3x plus 1, and then plus x, which is just change the sign in the middle, and then right here do the same thing. So square root of x squared plus 3x plus 1, and then plus x. So that's pretty much all we have. Now let's put on the parentheses. Okay, people, here we have the limit as x approaching infinity. When we do this times that, we just do this thing square, which is just the inside, and that's x squared plus 3x plus 1. And then we minus this thing square, right, which is going to be x squared. So that's what we have. And then divided by that, which is square root of x squared plus 3x plus 1, and then plus x. So far, so good. Okay, let me just write this. All right, now check this out. X squared cancel very nicely. This is the limit as x goes to infinity. We can do L'Hopital's rule because it's infinity over infinity, but don't do it. Why? Because we can do the pre-calculus way. And that is, look at the highest power of x on the top, and that is here. We have 3x to the first power. And look at the highest power of x on the bottom. It looks like this, huh? Well, this is x squared inside of the square root. So this right here, in fact, it's the same as that because both of them are x to the first power. Both of them are x to the first power. So this right here reduces to, just to take the limit as x approaching infinity. On the top, we get the 3x. Perhaps I'll put this down in blue. Over the bottom, this is square root and square cancel, but x is positive, so you don't need the absolute value, which is just x. So x plus x, we have 2x. Wow, what do we end up with? Of course, they cancel, so we just end up with the number 3 over 2. Yeah, so infinity minus infinity can give us a lot of surprises. Okay, 2 more questions. 13. The limit as x approaching infinity, e to the x times sine of 1 over x. Real quick, put infinity to here, we get e to the infinity, which is infinity, times, put infinity to here, 1 over infinity is 0, sine of 0 is 0, 0 times infinity. Is that just equal to 0? We can say a thing. We don't know yet, okay? We don't know. That is one of the indeterminate forms. So again, let's just go ahead and do the work. But we will have to change this to either 0 over 0 or infinity over infinity, right? Well, in this case, I'm going to bring the e to the x down. It's easier to work with the exponent. So check this out. Let's look at e to the x power. This right here, we can look at this as the limit as x approaching infinity. Keep this on the top. We have sine of 1 over x. But I will bring this down to the bottom and make that into a negative exponent, e to the negative x power. If you put infinity to here, you see e to the negative infinity is 0. Put infinity to here, we get 0 as well. And again, we'll just put this down to the bottom with negative exponent. But this right here, as we talked about earlier, it's 0 over 0, so we can use L'Hopital's rule. So it's all good. Go ahead and do ddx here and ddx here. So let's see what we get. We have the limit as x approaching infinity. Here we have sine, and the derivative that will be cosine, and the input stays the same. And remember, multiply by the derivative inside, which will give us negative 1 over x squared. Write this as x to the negative 1 power, and you'll get that. Differentiate the bottom, we get e to the negative x, but multiply by the derivative of this, which is going to be negative 1. So that's what we have. Okay, so, what do we do? Well, let's have a look. This right here is the limit as x approaching infinity. I mean, I can put this on the bottom, right? And I can put this on the top. So let's see. Here we get e to the x and then times cosine of 1 over x. All right? And then over x squared. And then negative cancel out already. So that's what we have. What's this? Let me tell you, the answer is actually infinity. And here is how we can do it. I'm not going to differentiate this anymore. Yeah, we did a lot of derivative already. Here is one of the limits law. What we can do is just pay attention to the limit as x approaching infinity. And this is e to the x over x squared. I put them right here first. And then I look at the limit as x approaching infinity of cosine of 1 over x. So the idea is that the limit of a product, right? I look at this times that. It's the same as the product of the limits, provided that if the limits exist. And this is really useful whenever you see like cosine of 1 over x. You know when x is approaching infinity, this guy is just equal to 1. So please do not differentiate this right here, because that would be really crazy. You can differentiate this twice. Let's do this in your head. Because this is infinity over infinity, right? Differentiate this again. On the top is still e to the x. On the bottom we get 2x. Do it again. E to the x on the top. And then we get 2. Put x to be infinity. We get infinity. So altogether, this right here is just infinity times 1. So the answer is infinity. Or you can use what we call the list, but that will be later on. But that's the idea. Just differentiate 2 more times. Yeah, that's it. But separate them though. Separate them. As long as you don't get like 0 or anything, then separate them is totally okay. Now, number 14. Yeah, time for the celebration. Do we need to bring the x down like that, things like that? Do we need to do things like that and then do L'Hopital's rule? No. This is why. Put infinity to the x here times this is inverse tangent of infinity. What does this approach? This is infinity. But what's this? This right here goes to pi over 2. Guess what? Infinity times pi over 2. Oh my god, I love this question the most because we can draw conclusion right away. Ladies and gentlemen, the answer is just infinity. That's it. Yeah, I put the easiest question at the end, but also it could have been the hardest question or the trickiest question if you didn't pay attention, if you don't do the check. this is not an indeterminate form. You get to draw a conclusion right away. Do it. Okay, so hopefully this helps. If you guys need more help, you guys can check out my other videos, subscribe to the channel so you can get more help in the future. And as always, that's it.